Okay, this is the third video for pressure. So a fluid is anything that can flow. Okay, so that could be a gas or a liquid, and we generally think of fluids as being a liquid, but it's also the gas. So we're actually living in a fluid right now. Now, any fluid can create pressure, okay, and that's due to its weight. Okay, so if you had an object sitting on top of you, okay, so that's you underneath that object, okay, that object would apply a pressure because of its weight to you. And that's the same thing with air, okay. If there's a box of air, then that would also create a weight, and it would push down on you, creating pressure, where the weight is the force, dividing that by the area of application gives you the pressure. We call this atmospheric pressure. When we go underwater, we have the air and water pushing down on us, and because the density of water is 1,000 times greater than air, it actually means that it's the pressure will be 1,000 times more powerful for the same height. So you actually need to go 1,000th of the height to get the same pressure. So for example, pressure increases the greater the amount of fluid above a point, the greater the pressure. Okay, so if you think about this point here in the cup, then there is a much larger distance to the top, so there's more weight pushing down on that point, so there'll be greater pressure. So the greater the height of fluid above the point, the greater the pressure. And that's the idea of these objects, okay, that you want to get water as high as you can for a town system to get the greatest pressure in your shower. This thing, the Mandelberg hemispheres, this shows you how strong air pressure is. Inside there's a vacuum, and vacuums do not create attraction. They do not create, there's no such thing as a suck, okay? It is a pushing force created by the atmosphere. So inside this hemisphere, or these two things joined together, inside there is a vacuum, okay, where there's no air pressure or very low air pressure. And then what happens is the air pressure outside wants to get in there, so it's going to push against the surface. Well, it always is. So the air pressure pushing against the surface is what makes it so hard to separate. So as you go underwater and so on, there's a thing called upthrust, which is actually due to the pressure on the bottom of an object is larger than the top. So there's a difference in pressure, and that can create an upwards force. We create a vacuum in our mouths when we are trying to suck up a fluid in a straw. Okay, we don't actually draw the fluid in, the fluid gets pushed by air pressure. So we create a low pressure area inside our mouths, and the high pressure outside pushes the fluid up into the mouths. So here the question is how tall can a straw be? Similar things with pumps, you create areas of low pressure, stuff gets pushed in. Vacuum cleaner, okay, there's your pipe, there's your vacuum. What happens is a vacuum cleaner creates an area of low pressure, there's high pressure on the outside, air gets pushed from the high pressure through the hose into the vacuum cleaner. It does not get dragged in, there's no physical force pulling the air particles in. Dams. So the whole idea of dams is you can get water to the greatest height to get the greatest gravitational potential energy. Remember, from GPH. Okay, and because of that height, you also then get the greatest pressure at the bottom. Now, If you look at the shape of the dam, why do you think it is in this triangular shape? Okay, why is it in a triangle like that? That's because there's greatest pressure trying to force in at the bottom than at the top. There's no point using too much concrete. So how do we calculate this pressure? Okay, so if we are given gravity, okay, so if we're given gravity, and remember that's measured in meters per second, we're given the density, okay, of the fluid, and we're given the height of the fluid, then the formula is pressure equals rho density multiplied by gravity multiplied by height. Height must be in meters, density must be in kgs per meter cubed. You could derive it. You could say that, hey, pressure is force divided by area. If I have a cylinder of fluid, certain area, certain height, certain density, well, what's the force? It's the weight of it. Now, weight or force, well, weight is equal to mass times gravity. So the mass of this thing is from density. Density equals mass divided by volume. So mass is equal to density times volume. So mass equals density times volume. And weight equals mass times gravity. So density times volume times gravity. Okay. In this case, the volume is actually area times the height times gravity. Chucking that in here, rho A H G divided by another A. Cancel those out. F of rho GH. This is AS work, that part. Don't need to know it. Just out of interest. Now, an example, if the air has a density of 1.3 kgs per meter cubed and atmospheric pressure is 10 to the 5 pascals, approximately how high is the Earth's atmosphere? So, pressure equals rho GH. So 1.3 is density times 10 for gravity times height is equal to 10,000. Oh, sorry, 100,000. One of zeros. So, working that out equals 7 kilometers. Just rounding up there. Oops, kgs, kilometers. Now, is that correct? Well, how high do planes fly? Very good question.